So I have one system that we're going to look at today. X plus y plus z is equal to 2. And 3x plus 3y plus 3z is equal to 14. And then x minus 2y plus z is equal to 4. Take that system of three equations and do these two tasks with it. Number one, graph it in GeoGebra in the 3D solver, just so that you can take a look at what these three systems represent. And then that should give you an idea of like what kind of solution you are going to get, and then try and solve it by elimination. And then we'll go over it. Today we have notes on the next section. Today we'll be talking about 9.3, systems of nonlinear equations in two variables. The notes for this section will be a little bit longer than normal. The math isn't that hard, but there's a lot of details to capture. Okay, in the meantime, I'll take attendance, and then as soon as I'm done taking attendance, we'll get started. How's it going out there?
Good.
Okay, 1 second. Okay, well, let's go ahead and get started. So who noticed what about the graph?
The first two are parallel.
Yeah, X and Z are parallel.
Yeah, I like that. So yeah, let me go ahead and switch capture over there. So like I said, the first thing that I wanted you all to do here was to go to GeoGebra and check out what these graphs are in 3D. So you'll notice here in the screen share that I swapped over to, this is our first function, x plus y plus z is equal to 2. 3x plus 3y plus 3z is equal to 14. And then x minus 2y plus z is equal to 4. And then I color-coded these out as being light blue, red, and green. And you'll notice that it looks like this, right? So we have two planes that are parallel, the red plane and the blue plane, so first and second equations. And then the green plane, that third one, it does cut through both of them along two lines. But when it comes to a system of equations, right, a solution to a system of equations, what is that solution supposed to represent?
X, Y, and Z.
X, Y, and Z that satisfies what?
The point of the intersection of all three.
The point of the intersection, and most importantly, of all three of them. And if two of them don't meet at all, then there can't exist a solution to the system whatsoever. Are there any questions there, like on that major concept? Or like questions about using GeoGebra?
So, Mr. Robinson, would the answer be undefined or no solution?
Those are not the same thing. The answer in this case is no solution. No solution exists. Undefined typically means that you're referring to some sort of mathematical object, which itself is undefined, like 1 divided by 0 is something that we consider to be undefined.
Okay.
At least until you learn calculus, then it gains some additional definitions.
Mr. Robinson, it's no solution because it's parallel? Or
It's no solution because it's parallel, yeah. Yeah. The solution to a system of equations is a location where all three of the equations intersect. And because two of these equations don't intersect, there can't be a place where all three of them intersect. So let's go ahead and show that mathematically, because just like how it's borne out by the graph, it should also be borne out by the mathematics, right? And so I'm going to start this off by attempting to eliminate x. And so in order to do that, I'm going to hit the first equation with -3. And I'm going to hit the third equation with +3 so that I can eliminate my x's. So if I do that, here's what my system of equations become. -3x minus 3y minus 3z is equal to -6. So that's 1, 2, 3. So here's what equation 1 has become if I hit it with -3. Equation 2 is going to be unaffected. 3x plus 3y plus 3z is equal to 14. And then equation 3 comes out on the other side after we multiply it by 3 as being 3x minus 6y plus 3z is equal to 12. Now I can go ahead and hit equation 1 into equation 2 and equation 3. So I would take 1 and add it to 2. I would also take 1 and add it to 3. But I'm not even going to get past this first step, though, because equation 1 plus equation 2 produces an interesting result. And this is kind of how we can tell that they're parallel. What happens on the left-hand side?
Everything cancels out.
It cancels.
Yeah, -3x minus 3x, 3y minus 3y, 3z minus 3z. The left-hand side of this sum just gives us 0. And 0 is apparently equal to what
8.
on the right-hand side?
-6 and
8.
Oh yeah, 8.
8. 0 equals 8, which it doesn't. This is a false statement. And as a result, we know that there is no solution to this system whatsoever. Oh man, I took the door off my computer and now the fan from my desktop is like blowing my notepaper around. That's annoying. Let me headphone wire. Let me put the cover to my PC back on so that it's not a problem. Stupid overclocking. Okay, anyway, so that's it for today's warm-up. Are there any questions on the warm-up as I awkwardly try and put my computer's door back on? Either questions from the homework or questions from the warm-up. No, we're all smart and we know how to do a math.
Yeah.
And Mr. Robinson, I have a quick question.
Yeah.
In the homework yesterday, there was a problem like this, but for the answer in the back of the book, it didn't put a no solution.
Just because it doesn't solve out nicely doesn't mean it's no solution. There's also the possibility that it's an infinite number of solutions.
So, for example, it just said X. There was no value.
Yes.
Oh,
So
yeah, I saw that.
if it's an infinite number of solutions, then the answer will be a line. Sorry, let me get the door back on this PC. Okay. Yeah. So if the answer is an infinite number of solutions, if you're in one of our rare cases, then the answer to the system won't be that you get an order set of 3 numbers. The answer will be that you get some equation, and the answer to that problem is the line y is equal to x. Let me pull up that slide with the 3 planes again. Okay, so do you see the screen I'm sharing with you?
Yeah.
Okay, so this one right here in the bottom left, this is kind of the problem we just dealt with for the warm-up. I have 2 parallel planes, and then my other plane cuts right through them. When it comes to solving a problem that has a unique solution, we're usually looking at something like this one here on the far right, where all 3 of the planes intersect, and they intersect at a discrete point that we can solve for. However, you have cases where the 3 planes do intersect, but instead of intersecting at a single point, all 3 of these planes here in this top image, they intersect along this line right here. And in those cases, the answer to, hey, where do these 3 planes meet? The answer to that question is, well, whatever the equation of this line is. You know that you're working with that kind of system because instead of getting what we got in the warm-up where it said 0 equals 8, right, which is a nonsense statement, instead what you would find is that 2 of the equations cancel out and give you back just a linear equation. So you would eliminate these 2 and you would just get back an equation. Eliminating 1 with 3 would give back the exact same equation, right? And then if you were to take those 2 problems and solve them against each other, you would get 0 equals 0. Whenever your final step is 0 equals 0, that's telling you that there's an infinite number of solutions, and you can present any of the linear equations that you had as the answer. And any of those surviving linear equations, if you took them and simplified them down, it would just simplify down to y equals x, or some version of that. Is that okay?
Yeah, I think.
Yeah.
Okay. Okay, so today we're going to go ahead and move along with section 3. Today we'll be talking about other types of systems and their various intersections. Today we'll be talking about 9.3. Let me get the proper title. Oh yeah, systems of nonlinear equations and inequalities. In 2 variables. Okay, so here's the over-under of this, right? What we're going to be talking about is systems of nonlinear equations now, as opposed to all of the linear equations that we've been dealing with in the last two sections. So in the last two sections, right, in section 1, we talked about linear systems in two variables, which is really easy to deal with a line in 2D. It's just a line, right, y equals mx plus b, equations of that form. And then in the second section, we dealt with linear equations in 3D, which in 3D, a linear equation doesn't actually produce a line. A linear equation produces a plane. But in both cases, we were using elimination or substitution in order to find the intersection of those systems. And the possible intersections are all really straightforward. It's either one solution if all of the equations intersect at one point, or it's no solution if we have some of our elements which are parallel, right? And as a result, they don't cross. Or we could have an infinite number of solutions if there was an overlap in our system. Like if our two linear equations were actually the same, then technically every single point along that line represents a solution to that system. Today, we're going to be talking about systems of nonlinear equations, which are equations that can take more interesting forms, things like parabolas or circles or ellipses or what have you. And in order to talk about these, let's just go ahead and start off real easy. Elimination doesn't work. So we must use substitution to solve these problems. Just right off the bat. And the possible number of solutions varies with the geometry of the objects in our system. Once we start introducing nonlinear elements, we have a lot more possibilities than just one solution, no solution, or infinite solutions. It all just depends on the type of objects within our system itself. So let's go ahead and run through a couple different possibilities, and for this part, we'll just be sketching. Here are some combined systems that we might have to deal with, but what we want to take away from this is not the specific answers, just how many solutions are there and why. So for this first one, I'm going to pop back over to Desmos. Can you all see the Desmos screen?
No. Yeah.
Yeah?
Yeah, now it's good.
Okay. And so right here in this first one, we have a parabola and a line, right? And how many places are they intersecting right now?
2.
Yeah, you'll notice here that we can get two discrete solutions because the line is capable of passing through the parabola in exactly 2 points. Those two intersections would be our solution. Or I could take the line and I could shift it down. And now how many solutions would there be?
1.
1. Or I could take it and I could shift it even further down. And now there would be no solutions to the system. Are there any other possibilities that I didn't cover? Nope, I think that's about it. So when it comes to the equation of a parabola and a line, our possibilities are 2 solutions, 1 solution, or no solution. And the best way to check which one of it's going to be is by graphing. So just take a quick sketch of those possibilities. I have a parabola, or if you want to condense your drawing at home, you can make one big parabola and then put a couple different lines through it. But when it comes to the outcomes for our parabola and line, it can either be 2 solutions, 1 solution, or no solutions, all depending on the relative position of our line. Is that first part okay? Yeah? No?
Yeah.
Yep.
Okay. So let's go ahead and take a pause here to do an example. And then I'm also going to do a TI-84 tutorial on this problem. So if you want to grab your calculator so you can follow along at home, I would recommend that. So for our first example here, we're going to solve for the intersection of a parabola and line. And so for example, what is the solution to the system? Y is equal to x squared minus 2, and y is equal to 2x plus 1. Yep. And so notice that first equation there, that's going to be what now?
Probably.
Yeah, that first one's a parabola because it has an x squared, but that second equation, well, that's just a line. So before we get into the maths of this, let me go ahead and graph it in Desmos so that we know what our answers are going to be. Ooh, not the whole screen, okay. And so I'm going to swap out this top one for y is equal to x squared minus 2. And I'm going to swap out the bottom equation for the specific line y is equal to 2x plus 1. And notice here, how many solutions do we expect to get when we do this by hand?
2.
We should get 2. And you'll notice that this is a high school algebra problem. And as a result, the answers are integer. So the answers that we should get should be -1, -1, which is an ordered pair. And then up here at the top, we should get 3, 7. So let's go ahead and talk about how we can get that solution algebraically. All that we're going to do is we're going to substitute these equations into each other. And notice both of these equations are already solved for what variable?
Why?
They're both already solved for y. So even though each one of these represents its own equation, substituting them is as simple as setting them equal to one another. So I can take these two systems and say that, well, if I'm looking for the place where they're equal, x squared minus 2 has to be equal to 2x plus 1 at that position. And so how do I solve for x?
Move 2 over and then move x squared over.
Yeah, this is a quadratic equation, so I need to take this and I need to set it equal to 0. In order to do that, I'm going to subtract 2x and I'm going to subtract 1 from both sides. So that's going to give me x squared minus 2x minus 3 is equal to 0. And now you'll notice that this guy factors. I need a number, sorry, I need a pair of numbers that multiply to -3 that add up to -2.
-3, 1.
X minus 3 times x plus 1 is my magic pair of numbers that does that for me. They multiply, give me back -3. They add up and give me back -2. And so I can take each piece of this and set it equal to 0, set this guy equal to 0. And this first term tells me that x is equal to 3 and x is equal to -1. Now keep in mind what we're looking for in terms of a solution to this system is ordered pairs. So this is only the x's. How do I get back my y's?
Plug in the x's into the one of the equations.
Plug the x's into one of the original equations. Which of these two does not matter as long as we didn't make a mistake up through here, because the whole point of this is that taking these and plugging them in here should give us the same number back for both. So 3 times 2 is 6 plus 1 is 7. So that should be 3, 7. And our second one is going to be -1 times 2 is -2 plus 1 is -1. -1, -1. And I believe that these points match our Desmos graph perfectly. And getting the answer is actually pretty short mathematically. Is this okay? Are there any questions on this, our first example?
No.
Yeah, pretty clear.
Okay, so let's go ahead and say that our answer is not integer because instead of this question coming from a high school math textbook, this question is from, I don't know, a college level calculus course, and we need to know where these things intersect, which you will run into in calculus. there is a thing called an integral, and to do an integral, you need the endpoints of where two functions cross. So I guarantee this is a skill that you'll be using again next year. Or even better, let's say that, you know, for some reason you're trying to find where two functions cross for the sake of a real life application question. It's very rare in those cases that the answer ends up being integer, right? So luckily your graphing calculator, and let me switch over to that. Your graphing calculator, do y'all see the calculator emulator?
Yeah.
Okay. And typing is, my laptop is a touch screen, so I actually think, yeah, I can just like touch it. Anyway, let's go ahead and say that we want to know how to do this in our own graphing calculator, mostly because if the answer is not a nice clean integer, your calculator can still get the decimal. So let's go ahead and start by punching in our two functions. And so the first function there was x squared minus 2. And then that second function is 2x minus 1. I can hit graph, and it should show us where these two intersect in real space. Now that's kind of a faraway picture, so what I'm going to do is I'm going to pick zoom in, enter. And also, before you hit enter again on zoom in to make it zoom in, wherever you put the cursor is where it will try and center the screen. So I'm going to try and center the screen around where the intersections are so that they're both in view. And beautiful. Okay. Now you can use the D-pad, of course, to click around, try and figure out where that intersection is. But if you actually want to know, what we're going to do is we're going to hit second, and then the trace button, because right up above that in blue it says calculate. And what we're trying to calculate is an intersection. So you can scroll down here to 5, or other fun fact, you can just hit the number 5. And it'll ask you, hey, what's the first curve? So we're going to try and get the cursor over here near the intersection. I'm going to hit enter. Second curve, again, just try and get the cursor close to the intersection, hit enter. And then guess literally means get the cursor on the intersection. I'm going to hit enter a third time. And after hitting enter for the third time, I've made a mistake because that is not the intersection. Did I punch something in wrong?
I think it's not -1, but +1. You put -1.
You are correct. Thank you. 2x plus 1, graph. That's fine. It'll give me a chance to go through those steps again. Most people don't get it the first time. So that'll be second calculate, option 5 for the intersect. And then we're just going to get the cursor over to the intersection, and we're basically going to hit enter 3 times. Once for the first curve, once for the second curve, and then once for the guess. There we go. And we get that the intersection is precisely 3, 7. So long as you can get your equation in the form y equals, your graphing calculator can give you back that point. This is super useful next year when you're in calculus, where you won't be expected to show the work for the step, but you will need to know that one of your intersections is 3 just to be able to do the rest of the problem. Are there any questions here? Yes.
The first two enters were different. Why?
You are selecting first curve and second curve. So the only way in which those first two enters would be important is if, let's say, instead of having 2 graphs on here, you had 4 or 5 graphs all entered at the same time. It's just telling your calculator which graphs you're asking the intersection of. But if you only have 2 curves, they're basically irrelevant. Does that answer your question?
Yeah.
Okay. Now let's go ahead and talk about our next 2 classes of function sets that we might be asked to solve for the intersection of. Let's say that we have a circle and a line. Yeah. Let's say that we have a circle and a line. And for this one, instead of drawing multiple circles, I'm just going to draw one big circle and talk about the different cases that we could have across it. So here is my circle. Great. And so here are the possible outcomes I could have if I happen to have a circle and a line in the same graph. So here's my circle and line orientation, right? And just so y'all know, in case you forgot, the equation of a circle is x squared plus y squared is equal to radius squared. This gives us a circle which is centered at the origin. It could also be centered elsewhere if we took our equation and manipulated it. To do that, I would have to add terms h and k. So it'll be y minus k quantity squared, and I'll add a slider for k. And then it could be x minus h quantity squared, add a slider for h. And now I have a circle that can be anywhere. Oops. So one of these shifts it up and down, the other one shifts it left and right. I'm sure you all remember this intensely from that project where I had y'all draw some art using functions, yeah? And
Yes.
so when it comes to our possible intersections, here's what's going on. As it is right now, I have no intersection between the line and the circle at all. If I move this in, now I have one intersection, or maybe it won't let me do it, but you get, oh, there we go. Here we have an intersection of exactly 1 point. And then if I move the line all the way in, we could have at most 2 solutions. So there are 3 different outcomes for an intersection of a circle and a line. So let's go ahead and add those to our notes real quick. It could be no solution. It could be 1 solution. If it touches right on the edge and is tangent to the circle, so this is 1 solution. Or we could get the more interesting case where the line cuts through the circle here and here, and that one gives us 2 solutions. And again, just like before, the trick here is substitution, so you would have to be given the equations of both of these. You take the equation for the line, plug it into the equation of the circle, that will make it a quadratic, and depending on how the quadratic factors out, you'll either get 2 roots, 2 solutions, 1 root, 1 solution, or you'll get that quadratic only gives back imaginary numbers, in which case it's no solution. You'll see a question like that in the homework, and that'll be our warm-up for tomorrow. I don't want to meditate there. We have one more set of diagrams that I want to get through, and we'll look at a problem of that type. Is this diagram okay?
Yeah.
Okay. And then the final class of systems that we want to be able to deal with are, well, what happens if we have a circle and an ellipse? This one is much, much wilder. This one is a lot harder to notate simply because of how many additional solutions there are. So again, let me toss us back to Desmos and take a look. Okay, so here I have an equation of a circle, and this circle is locked on the origin. Wait, I'm sorry. Can y'all pause real quick? I hear cat-related chaos going on in the hallway. I'll be right back. Sorry about that. I think they were fighting for territory and then they ran away when I opened the door. Hey, anyway, y'all see the circle and the ellipse, right? Circle's red, ellipse is green.
Yeah.
Yeah, okay. So here we have a bunch of different possibilities. You'll notice that this circle is locked at the origin. It doesn't have an h and a k to recenter it. It only has a radius. And then this is the equation of an ellipse. It's very, very similar to the equation of a circle. And it actually is the equation of a circle if a and b are exactly the same. So you'll notice here if I reduce a down to 1, so that a and b are both 1, right, these terms in the denominator, then the equation of an ellipse will draw a perfect circle. But if a and b are different, then we get an ellipse, right? It's a different length in each direction. Now notice the way that it's drawn right now. How many solutions are there?
0.
None.
None. They are not crossing anywhere. So that is a possibility. Here's another possibility. How about now?
1.
A 1.
1, exactly 1 and 1 only.
Or
How about
B.
now?
2.
Now we're at 2 possible solutions.
4.
Wait, how about now?
3.
3.
3, we have 1 solution, 2 solution, and well, this should be just 1, but you get the idea. 3 solutions. Yeah, we could also totally have 4. And that basically maxes us out on the possible number of solutions. So in the case that you have a circle and an ellipse, we could have a 0, 1, 2, or 3, or 4 solutions, depending on the physical layout of the circle and the ellipse. So for this one, I'm going to draw a couple different circles. 1, 2, 3, 4. Oh no. I was stunting too hard trying to show off one-hand compass skills and I made a mistake. Nonetheless, we got 5 circles, unlike the Olympics, which are no longer happening this summer. And in my 5 circles, I could have a system with no solutions. I could have a system with 1 solutions. I could have a system with 2 solutions. I could have a system, and this is my favorite one, that has an odd number of 3 solutions. Or I could have a system with 4 solutions. And again, whenever you're working on a question like this, you could always check manually to see how many answers you have. Or you could, or you could just do it algebraically and the algebra will bear it out. Are there any questions up through here? Are y'all ready for an example of circle and ellipse, and then we'll stop here for the day?
Yes.
Okay. So for example, let's go ahead and say that I have 4x squared plus y squared is equal to 13, and x squared plus y squared is equal to 10. So what is the form of my first equation here?
They're both circles.
Only
the first one's an ellipse.
The first one is an ellipse, yeah. And here's how we know. That second equation is definitely a circle because x and y, the 2 things I'm about to say are technically the exact same thing. The second equation has no multipliers on x and y, or more importantly, they both have the same multiplier, which is 1. However, what do you notice about that first equation?
Has 4 as the multiplier for x.
Yeah, there's a 4 on the multiplier for x squared, and this is not the way that you'll typically see an ellipse written, right? Usually the way that you'll see it is that those terms will be in the denominator. But if I took this first equation and I divided everything by 4, that would give us x squared plus y squared over 4 is equal to 13 over 4. This is the way in which you normally see an ellipse written. So let's go ahead and start off by graphing it. Let me have y'all graph it in Desmos just so that y'all can get used to that, and then you can see how many solutions we're working towards. And I'm gonna go look at the cats again because they're making, like, don't get me wrong, the cats are constantly making crazy noises, like they sound like little horses galloping around. but they're particularly vocal right now, which is weird. Let me go make sure they're not like killing each other or eating string or something stupid. Like, yo, I'm not trying to go to the vet right now, you know what I'm saying? Like, it sucks going outside. All right. Did y'all see that cat? No.
Yeah.
Nobody.
Yeah.
Oh, what?
Yeah,
What?
we saw.
What a cat, dude, right? What a cat. Hey, anyway. Did y'all get it graphed in Desmos? What did you find?
There are 4 intersections.
Yeah. So let me go ahead and show y'all. And the reason why I like Desmos is, man, Desmos is not picky. Desmos doesn't really care how you enter the equation. It'll graph it no matter what. You could graph these equations in your graphing calculator, except your graphing calculator is very sensitive and very picky about how it wants its data. I'll show you how to graph this in your graphing calculator. You won't like it, but nonetheless. Yeah, we graph these two and we can see that we should get 4 intersections here, 2 up here and 2 down here, yeah? Let's go over how to solve this algebraically. And again, it's probably a little simpler than you think, yeah? And so all that we're gonna do is we're gonna use a little bit of substitution to get the answer here. Which variable would you like to substitute across? Would y'all like to substitute across X or Y?
Probably X.
Okay, yeah, we can totally substitute across X. So I'm gonna take my first equation and I'm gonna set it aside. We're gonna use him as is. So this is gonna be 4x squared plus y squared is equal to 13. And so I'm gonna take the second equation and I'm gonna solve it for X. And so if I were to do that, the second equation is gonna give me that X squared is equal to 10 minus y squared. Is that okay?
Right. Actually, probably Y.
Yeah.
I thought you were talking about the X squared plus Y squared over 4 because like this one, but never mind. Doesn't matter.
This equation and this equation are the exact same equation, like I said
Yeah.
at the top. The only reason why I write it this way is to show you how it like fits the standard form of an ellipse equation. But in terms of solving, this is a lot easier to play with.
Okay.
So no, that's a good question. And so now that this is solved for x squared, I could theoretically take the square root of both sides and get that, well, hey, x is equal to the square root of 10 minus y squared, and then plug that in here. But what's going to happen when I take the square of a square root? What happens when you square a square root, y'all?
We'll cancel the square root.
Cancels out.
It's just going to cancel the square root anyway. So honestly, there's no point in taking the square root here. We might as well just leave this as x squared. And since this is giving me a redefinition of x squared, I can plug it in right here and we can solve for y right off the bat. So I'm going to take this, I'm going to plug it back in over here. So this is going to give me 4 times 10 minus y squared plus y squared is equal to 13. And now we can go ahead and we can solve for y. Are there any questions on that step of substitution? So this is now going to work out to 40 minus 4y squared plus y squared is equal to 13. I'm going to subtract 40 from each side and I'm going to combine these like terms. So here on the left-hand side, I'm going to get negative 3y squared, and that's going to be equal to, what's 13 less 40?
27.
Equals negative 27, and then I'll divide both sides by negative 3. Y squared is equal to 9. I hit both sides with a square root, and y is equal to,
plus or minus 3.
Thank you. You stopped me from having to do the math teacher thing, which I'm sad is like a meme of math teachers yelling about the importance of the plus minus here. But yeah, it is crucial that we have both a +3 and a -3. Are there any questions there? Is that okay?
Mr. Robinson, so
Yep.
would you have to do it twice, like plugging it back in, once with +3 and once with -3?
Yes, except you'll notice that there's no difference because both of them will get squared.
Oh, okay.
Yeah, so you plug in 3, you square that, you get 9. You take -3, you plug that in, you square it, you get -9. It doesn't really matter. So we'll take this and we'll plug it back in here because this guy's already solved for x. So this is going to give us x squared is equal to 10 minus the quantity of 3 squared, plus or minus, it doesn't matter. X squared is going to give us 1. And again, I take the square root because it's 10 minus 9. And again, I take the square root right here. And so x is going to be equal to plus or minus 1. And so what are our answers?
1, 3, -1, 3, and then
1, -3,
1,
1, 3.
-3, yeah, and 1, 3. Or
And -1, -3.
Yep, all 4 possible combinations of these 4 values are answers to this problem. And a weird picky thing, but when you have multiple ordered pairs in a list, please separate them with semicolons. So yeah, for this one, we do a little bit of substitution. We solve like normal, and we find that, hey, there are 4 elements to our solution, because this is that case where the ellipse crosses the circle at 4 different ordered pairs. Are there any questions here with this system? Is this okay?
yeah,
Yep.
Okay. So just so y'all know, we're not quite done with notes just because we didn't get to inequalities. So tomorrow, and y'all have dealt with inequalities, it's what you think it is. You graph and then shade in the correct direction. We'll go over that tomorrow just so that we're all on the same page. But the last thing that I wanted to talk about today before I post the homework is just, well, how can we make our calculator graph this one? Because a lot of people have a hard time graphing things other than lines and parabolas in their graphing calculator. Let me show you why it's really hard in this case, but it is possible in case you ever had to do it. So one more time, here's a look at our 2 equations, 1 and 2, right? However, if we go to our graphing calculator and we're like, hey, buddy, please help, please do graph, right? I go to on, and then I go to the place where I punch in the equations, and what do you notice about the place where I plug in the equations?
It's only set for
set
y.
equal to y, yeah.
Yeah, it's only y equals. So if you want to feed this to your calculator, you can do that, except we're going to have to do a little bit of hand math first. I got to take this equation, I got to take this equation, and I have to set them both in terms of y equals. So this first equation is going to become y is equal to the square root of 13 minus 4x squared. To follow along with what I did, all I did was I subtracted 4x squared to the right side, and then to get rid of the square on that y, I hit it with a square root. And keep in mind that we're smart, calculators are dumb. We know that square roots have a plus and minus. Your calculator doesn't know that, so we'll have to tell it that manually. And then the same thing is going to be true of the equation of the circle. We can graph that in our TI-84, except the calculator is dumb. So we'll have to tell it that, it's not x squared plus y squared is equal to 10. Y is equal to the square root of 10 minus x squared. And again, I have to tell it that, this is a plus and minus. There's the top half of the circle and the bottom half of the circle. Are there any questions about how I could take those first 2 equations and remanipulate them into the form y equals? That part should just be algebras, yeah?
Yeah, pretty good.
Okay, and here's why we care about it. We can plug in these 2 functions into our graphing calculator, except our graphing calculator needs to take them as 4 functions. I'm going to start off by taking the square root of 13 minus 4x squared. And the calculator doesn't know that square roots have negatives. We have to tell it, hey, I also want the bottom half of this ellipse, which is going to be 13 minus 4x squared. And to get the circle, this is going to be equal to the square root of 10 minus x squared. And again, it doesn't know that square roots have a plus and minus, so I have to manually put in the bottom half of the circle, minus 10, or sorry, square root of 10 minus x squared. And the calculator is going to draw these in 1, 2, 3, 4. So the order in which you'll see these drawn in is going to be the top half of the ellipse, the bottom half of the ellipse, the top half of the circle, the bottom half of the circle, in that order. So let me go ahead and hit graph. Top half of the ellipse, bottom half of the ellipse, top half of the circle, bottom half of the circle. Now, this looks terrible for a couple different reasons. Keep in mind that the window is not like a computer screen where it's going to preserve the aspect ratio. If the scaling is stretched, this will also be stretched. So I'm going to change x min to minus 10, x max to 10, x scale to 1, y min to 10, y min to minus 10, and then y max to positive 10, just so that we get a nice unstretched graph. And that's much closer to what was in Desmos. Are there any questions here on section 9.3? Is this okay?
Mr. Robinson, can the calculator show us where they intersect?
Yep, just like the same as before, and I'll let you fiddle with it because we're out of time. But if you ask again tomorrow, if you can't figure it out, we'll go over it in warm up. It's just
Okay.
second calc intersect, go through the exact same steps, and it'll give you all 4 points. Except again, it's not Desmos, so you'll have to do it one at a time, and it's ugly.
Okay, thank you.
Yep.
Mr. Robinson,
yeah.
will you ask us to graph ellipse and circles?
Not by hand. If I asked you to graph them, you would have access to a utility. Though, to be honest, if they're centered at 0, it's pretty easy. I can talk about that tomorrow too. Yeah. Okay. Okay. I'll end it
Mr.
here.
Robinson,
Yes.
I have a quick question about this isn't really relevant to what you just said, but a Windows Lab Edition MSI, is that like a separate computer?
Send me a link.
No, because I have to download a lockdown browser on College Board, and it's saying lockdown browser download options. Is it a Windows Lab Edition or a Windows Lab Edition MSI?
I
Which one's your computer?
don't know. Again, send me a link. I don't know the answer to your question. I'm not sure what you're asking. Anyway, I'll post the homework. Y'all have a nice day, and I'll see y'all tomorrow morning for warm-ups.
Wait, Mr. Robinson.
Yep.
When did you do roll? Because I joined like 4 minutes after you posted the link.
I will fix it.
Okay, thank you.
Yep. Anyway, y'all have a nice day. I'll post the homework momentarily, and I'll see y'all tomorrow morning for warm-ups and just a little bit more notes on how to graph and shade inequalities properly.
All right, see you, Mr. Robinson.
Peace. Take it easy, y'all.
See you.